Hello everyone, welcome to our daily physics problem, day 14. So today we are going to look at a magnetic field problem. I know it's a big jump. We're going to use a lot of calculus today. You're welcome to use a calculator on internet to let you calculate the integral. Don't try to solve all the integral on yourself. So consider a straight wire of length L. L is a lot bigger than x. That has a current I flowing in the wire. The direction of the current does not matter. What is the vector expression for the magnetic field due to the straight wire at a point that does not lie on the perpendicular bisector of the wire? So here on the left picture, we already laid out all the integration and vectors variables that you need. So I want you to pause the video, try your own. After you try it, come back to the video and I'll show you how I did it. So welcome back, guys. So let's first recall our equation for our magnetic field. Because of the superposition identity of magnetic field, we can express it as a constant mu 0 divided by 4 pi times the integral of the source times I ds times the cross product of r hat, the unit vector for r, the position of the source to the position of the field point, divided by r squared from S to P, the source to the point. Then we need to express ds r hat and r sp in terms of the thing that we know in the picture. This is a general formula. Let's see how we express this. So first, the ds will be just dx prime times I hat. Let's define dx prime as the x prime as the position from the origin to the source, and it's in the I hat direction. Then r hat will be the unit vector from the source to the field point. That will be the vector divided by its magnitude, as we see above. Then how we express this in terms of x and y and x prime. So we know the vector of r is equal to x times I hat plus y times j hat. Then r prime vector will be equal to x prime times I hat. Then we divide by the magnitude of the vector, which is using Pythagorean theorem. Then we simplify it. On the top, we have x minus x prime times I hat plus y times j hat divided by x minus x prime square plus y square and all of square root. And that's our unit vector for the position vector from the source to the field point. Then what is the magnitude square of our position to our field point? We use some Pythagorean theorem. We know the distance between the horizontal distance between is x minus x prime square plus y square, all of them or square root, then I square them. Because we square root them and then square it, just come back to original equation. So we have our answer for the r square. Then we just plug them back into our original equation. I is a constant. So let's integrate it from the negative L over 2 to L over 2, because we can see the wire and the coordinate system is at the middle of the wire. Then we just copy and paste to plug them back in. We have dx prime times I hat to the cross product of r hat, the unit vector, all of them divided by the r square, which we copy and paste here. Okay, now let's solve the integral. Oh my gosh, integral is multiple variable and a cross product. It's a vector calculus. So let's simplify this. Let's first solve the cross product. Because these two terms are similar, let's just group them together. Let's only focus on the top terms. So we know I hat times I hat equals 0. And the cross product. Forgot. That's the cross product. Uh, this is a bad notation. Then I had the cross product of j hat equal to k hat. So we have I times j, we have k, and then we can ignore the x minus x prime term. Then we also grouped the denominators together. We have this expression here. Then we simplify it furthermore. You know that y is a constant, we just move to the left, then we just write everything on the right hand side originally, and then times in the positive k hat direction. So now let's solve for the integral. This is a very hard integral. So let's look at the integration formula. Usually if you have exam or homework problem sets, professor will put up a chart for integration, because we don't need to solve all of your own. You're really out of the field. So we know the integral of this function below is equal to negative times negative of x minus x prime divided by x minus x prime squared plus y squared, all of them square root, times 1 over y squared. Then we integrate it from negative L over 2 to L over 2. We plug them in. We have negative x minus L over 2 divided by x minus L over 2 squared plus y squared, or all of them over square root. Then we minus plug in the L over 2 ordinary equation. We have this expression. Then all of them times the 1 over y squared. So now let's plug it back into our magnetic field equation. Let's just copy and paste for the sake of easy. Then we have this expression here. Now let's try to simplify it a little bit. We know there are there are y squared and y. Let's just cancel them out. We have mu 0 I over 4 pi y times x minus L over 2 divided by square root of x minus L over 2 squared plus y squared plus x plus L over 2 divided by square root of x plus L over 2 squared plus y squared. And then, wait a minute. I think I did something mistake. Maybe in the integration, I forgot about the plus and minus sign. Yeah, this should be a plus sign. Sorry for that. This should be a plus sign. This should be a plus sign, and this should be a minus sign. Yes, because we minus a negative number. Because integration we minus a negative number, we should get a positive number. So this is an important result to remember. You shouldn't remember because it's too messy, and we want to find for L approach infinity. L is a lot bigger than x. So maybe when we choose the limit of the function, the equation will be a lot simpler. Because L is a lot bigger than x, we can just ignore the x, and also we can just ignore the y too. So after ignoring them, we can simplify it to negative L over 2 divided by the square root of the square of L over 2 minus L over 2 divided by the square root of L over 2. L over 2 just cancelled out, and the square root just cancelled out. We have negative 1 minus 1 is negative 2. So let's plug it back in to our original equation. We have negative 2 times negative mu 0 I divided by 4 pi y. Then 2 cancelled, negative 1 and negative 1 cancelled. We have mu 0 times I divided by 2 pi y. And that will be our final solution. K. Oh, we also need to put our vector direction, which is positive k. And that's our final solution.